It will be an environmentalist talk. Today we will talk about cleaning the garbage, and the ambience of the room is well aligned. By chance, welcome. And it's the destiny of front row, I guess. It's always empty. Yeah, welcome. So, everybody has a smartphone, I guess. And most probably some of you has some smart watches. And also, we are software developers. We are dealing with computers all the time. Maybe some of you has some self-driving smart cars. These are all possible with my company. This is ASML, the most important tech company you never heard of. We are producing the machines which produces the fancy chips you use all day and I use all day. iPhone chips, Samsung chips, everything. And our main partners are Intel, Samsung, TSMC, Micron for all kind of fancy stuff. This is my company. But who am I? By trade, I am an electrical engineer. And I made a mistake and I have completed a cryptography master's. And then I started working for a defense company. It's a government organization, actually. I worked for 15 years in interesting projects. And I joined ASML, my company, in 2018. I can tell that I am a polyglot developer somehow. I am exposed to multiple JVM languages and C, C++, MATLAB back in the days. And I'm dealing with 2 kids, trying to deal with their language as well. And they create a lot of garbage. But our garbage collector is generally my wife and sometimes me. But we will see, we are single-threaded. That's the problem. So why do we care about garbage collection? Why this talk? Because these are the recent results from GitHub Popularity of Programming Languages. They just released this last month. You can see in the top 10 languages we use in development, or the last year, the new repositories created in GitHub. Just 3 of them are not garbage collected, and for historical reasons. C++ is the improved version of C, we can see it, and Shell is completely different domain. Generally, it's a bit hard to understand problems with garbage collection. Maybe it's sometimes obvious, but generally it's a bit hidden. How can we tell? It's obvious if we get this kind of a nice message, if we are lucky, or sometimes we see some log message in our logs. We have a problem with memory. Okay, how can we deal with it? Maybe it's a bug in our code, or maybe we configured wrongly our garbage collection system. But sometimes we see the stuff happening in our production. The response rates goes down and the application gets slower and slower over the time. But I think we should first define what a garbage is. This is also garbage, if you know. When I was in college, I was listening to them. They have really cool songs. But these are all definitions of garbage. What today we will talk about the definition in the computing world. The unwanted data in our computer's memory. We don't want to deal with this data. We don't care about this data. We want to get rid of this data. But how can we do it? This is a basic Java code. Its job is just some integers, and somehow we want to log or output the result when we are dealing with it. We can see some garbage here. It's obvious. This is the garbage. At each iteration, we are creating a string object, but since string is immutable in Java, we don't change the same object, and we allocate another one for the next run. And if our loop is a long one, then we are creating a mess. We should talk about the origins. Where is this coming from? this garbage collection idea? Actually, this is our biology. In our brain, we have the garbage collection system. It's called brain waste disposal system. And we have a nice fluid in our brains which is only released when we are sleeping. Cerebrospinal fluid. And in that sense, we can say that sleep is important. With our chemicals producing with our nucleus or all the stuff happening in our brain, there are many waste which is generated. And the only way to deal with this mess is this fluid. This guy is also dealing with garbage in his own sense. He is trying to collect the garbage. But how do we clean the computer garbage? This is the old way, as known as manual memory collection. So if you use C, C++ kind of languages, old C++, then most probably you created your own memory location. In C++, it's not like that, but in C especially. You malloc created a memory location with malloc, then you need to free that memory. This is the manual stuff. We have to do it ourselves. Or we can do it automatically. We can give the job of garbage collection stuff to compiler or our platform. And there are two ways to do it. One is automatic reference counting, and Swift is one of the most modern languages. But for historical reasons, they chose to use automatic reference counting and also some performance reasons we will see. And with the new C++, there is shared pointers which can automatically count the references and it can free. And the second way of doing automatic garbage collection, memory management actually, is garbage collection. It's Java, C#, and all the 7 of top 10 languages. There is a nice code. So freeing and allocating a memory is so important in C, C++ authors that they thought that it should be the responsibility of the developer. And we can see this is an old kind of C code. We are allocating a string. It's 25 bytes. We are putting some value into this memory location. Then we want to use the same string or same memory location again. We are reallocating it with a different size. If we know what we do, then it's okay. But if we size it wrongly, then it's a mess. We can write to wrong memory location. It's a security breach. It's all kind of problems. And we are responsible for it. But this is the most performant way of doing memory management. And there is another world. In Java and C#, the authors of the language saw, okay, maybe it's so important, the memory management stuff is, it shouldn't be left to the developer itself. It should be managed by the programming language or the infrastructure. And this is the same code. Not exactly the same code, it's Java. So we are allocating a string in the memory. We don't even know we are allocating anything. Behind the scenes, our garbage collection system is also responsible for the allocation. And there is a downside in Java kind of languages. We cannot reach the actual memory location like in C. But do we care? I don't think so. And we are reallocating the same memory. And there is no freeing, no hassle. So it just works. Anybody knows this gentleman? I'll give you some hints. He is the father of artificial intelligence, and he is the creator of Lisp, and he is the creator of first garbage collector, and he is the recipient of 1971 Turing Award. It's the most prestigious award in computer science. This is Sir or Mr. John McCarthy. Why do we need a garbage collection? So it's just giving the responsibility to some other system which can do it better actually. And also automating is nice because we are developers and we are lazy. And also it prevents human errors. That's the most problematic concept. And also it will minimize our possible memory leaks. Of course, it doesn't mean that in Java and C# we don't have memory leaks. We can create memory leaks, but it's a bit harder. And it increases the developer productivity. If you remember, JavaScript was the #1. Is it good on performance compared to C, C++? No. But it's the most maybe productive language because you can find everything. All kind of libraries are there. This is the same list again. So why some programming languages or platforms doesn't use garbage collection? There are some historical reasons like C++ or Swift, because C++ is coming from C. It was not garbage collected. Swift is coming from Objective-C. It was not garbage collected. There are some performance problems. We will see garbage collection is nice, but it brings its own kind of problems. And its predictability. So garbage collection is some kind of a system. It works behind the scenes without you knowing it works. And without you knowing, it just stops your application and it handles the mess for you. But sometimes it's a bit unpredictable. Maybe there is an alternative for garbage collection kind of automation. Automatic reference counting is the biggest alternative for automatic memory management in compared to garbage collection. This is a Swift code. So we have a user, and our user has a list of phones, and the phone object knows its own user. If you take a look, there's a cyclic dependency between the objects. So automatic memory management or automatic reference counting means if the count of a reference in one object drops to 0, it's treated as a garbage. But in this case, none of them will be 0. They have a cyclic reference. How do the language authors deal with this situation? If you use C++, new C++, there are some weak pointers and some stuff in the language. It's the same concept. So this problem is called retain cycle problem. Still, as developers, it's the developers responsible to deal with this problem. You have to use some string, some interesting keywords. You have to say that, okay, this reference is strong, but the other reference is weak. I don't care about this reference. So you can treat it as 0 when you try to collect the memory. We can still make mistakes in this way, and we can still create memory leaks. And the way of garbage collection, in as far as I know, all the garbage collected languages, there is no retain cycle problem. It just works. How does it work? In this picture, we can see that there are some complete cycles, but the way Sir John McCarthy suggested, it's called mark and sweep algorithm. We will define it. It just starts from some important node. It's called garbage collection routes in JVM world. And it just visits all the nodes coming from that root node. And if it visits a memory location or object, it's treated as non-garbage. So there is a reference to it. It's not garbage. If it cannot find a node, it doesn't visit a node, then by definition, it's a garbage. So we can compare these two. Automatic reference counting is performant. It's deterministic because when you go out of a scope of the memory or any loop, then automatically compiler generates the freeing code for you. It's deterministic. You know when it will be triggered. But in GC, it's not deterministic, and it can block your application. Like the kids creating a mess in the living room, then the mom goes into the living room, stop. Go out, I will clean your mess, then come later. This is the garbage collection stuff. And it requires additional resources. Somebody should be responsible for cleaning the mess. And it will require some additional CPU time, it will require some additional memory because we will see that it's actually a complicated work. But the problem with automatic reference counting is it cannot cope with retain cycles as well as garbage collection systems. We need to deal with it. And garbage collection is, in the same sense, just works. You don't have to do anything. Yeah, you have to tune if you make a mistake. And Objective-C and Swift, in that sense, are examples for automatic reference counting. And Java and C#, as we know it, are examples for garbage collection systems. Productivity versus performance is the problem, or the trade-off, let's say. But we can see that in the trade-off GitHub popularity in the languages, it's going towards productivity, not for the performance. If you talk to Linus Torvalds, of course, most probably he will call you stupid. But most probably we are not talking to him, and we are not kernel developers generally, so we are safe. So let's think that we want to design a garbage collection system. What are the requirements? The first step is to create some functional and non-functional requirements. The only functional requirement of a garbage collection system is dealing with memory allocation and deallocation. We can boil it down to this one. The others can be treated as non-functional requirements, but as we know as software developers, non-functional requirements are the actual requirements which defines your architecture and system design. Throughput, latency, and memory layout constraints are the important ones, in addition to the functional requirements. Functionality is okay. We also talked about this one. In the system, there are some root nodes. The system starts visiting the nodes, beginning from a root node, and if it visits a node, it's okay, it's not garbage. If it doesn't visit a node, it's treated as a garbage, basically. That's all. This is the functionality, mark sweep algorithm, defined by John McCarthy. And in JVM world, garbage collection routes the important objects, which is always treated as live objects, are static objects. So we should be careful using statics. And they are the active Java threads. Active Java thread is always reachable. The references coming from that one is always treated as a garbage collection route. And some native code. And this is what happens behind the scenes, actually. We can see in this animation, it starts visiting the nodes. If it can find a node coming from a root, then it's okay. Its bit or mark bit is set to 1, it's reachable, and the others remain 0. Basically, after this marking cycle, we already know which object is garbage and which object is not garbage. We will see also concurrency is a problem in this case, but it didn't start with concurrency. Life was simple and easy. And this is the non-functional requirements, the important ones actually. The most basic one is serial garbage collector. So it only has one thread, like I have only one wife, cleans the mess of the kids. And then they made an improvement somehow. There are some helpers to my wife, but kids still needs to stop playing and the cleaning should be done. And then they also increased that part. They said that, okay, we can maybe decrease the stopping the world portion. This stopping or pausing is called stop the world. And we can maybe do the marking stuff, determining which is garbage or not stuff concurrently with your application. You can continue playing and creating some mess, and at the same time, somebody can visit the nodes you already create. And memory layout. So back in the days, I was using Windows disk defragmenters. We didn't have SD kind of speedy hard disks. We had mechanical hard disks. And if your hard disk layout is fragmented heavily, then your response rates would go up, 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 and basically I was a computer player, then I was not able to play my nice games. And this is the same concept. If we create an string object in this example, and if we append something to it like the previous example, we basically create one object, then in the next cycle it's just garbage. We create another one, and it goes on and on and on until garbage collection decides that, okay, I should deal with the old memory, I should clean it, then maybe we can fit some nice stuff in it. If we had this kind of a picture, which we have scattered memory locations and there are not enough contiguous memory location, then if we want to allocate a big memory, then we are in trouble. So this is called compaction in garbage collection world. This is also one of the very important aspect of garbage collection. How do we evaluate the garbage collection? So it can be performance. We don't care about the functionality because we also treat that functionality will always be there. Pause time. So the garbage collection stops the application, and if your application is paused for 10-15 seconds, in this world you are in trouble because the user cannot get any feedback or any response from your system. Your system is basically by definition not responsive. Pause frequency. Maybe it doesn't stop your application that long, but it stops frequently. It's also another problem. And the pause distribution, maybe in your hottest hours in your application or your system, the garbage collection kicks in and just stops your application. Then you will lose customers. And maybe you're allocating too fast that your garbage collection system cannot cope up with your speed. You allocate, I don't know, 1 gigabyte per second, but your garbage collection is able to only clean half of it. Then eventually you will be out of memory. Concurrency. Concurrency brings its own expense. Maybe if you want a responsive system, it means that when garbage collection system kicks in and starts cleaning your mess, your application should continue working. It should be responsive. Scaling. If you want to increase your memory in your system, how will your garbage collection system behave? We will see that they started from basics and it's improved in that sense a lot. And it can take a lot of CPU time. So it can basically steal your application's resources. Memory footprint is important if you want to deal with huge memory. But we should see how memory works. In a typical computer, we have a kernel, which is the heart of your operating system, which does everything important stuff for your operating system. And to help the kernel, there are some system applications, some utilities. And of course, as a user, you want to use your maybe office applications, maybe you want to play some games, or you want to browse the web, you will be some applications using. And then in JVM, if you have an application, then it's the only usable memory, the rest memory of your system. And there's a rule of thumb, it's like 80 to 20%. If you have 10 gigabytes of available memory, you can only give 8 gigabytes to your JVM. The 2 gigabytes should belong to kernel and system applications and other applications at least. And we should go also deep dive in memory terms, stack and heap. This is an example Java code. Stack belongs to one thread, and one thread contains the primitive variables and also object references which are created by our code. The actual memory allocation happens in heap. The concepts are different. So stack is used by only one thread, and heap is a global memory. And also stack is reclaimed when the thread exits, but heap is a bit complex. We need some kind of a garbage collection system to move all the nodes and visit all the nodes. And stack holds our primitive variables like ints, bytes, or our references to objects which we allocate in our heap. And stack is easy because the early computer systems designed by only using stacks, it's last in, first out. But heap is not like that. Heap is like a sack of memory, it's unorganized, it's complicated. And when we are out of stack space, we will get a stack exception in JVM world, stack overflow error. And if we are out of heap, then we will get out of memory error. And we should talk about generations first. How JVM guys designed their garbage collection system. Do you recognize this picture, this plot? By empirical analysis, early computer scientists came up with this observation. Most of the objects becomes just that. And generally, the ones who lives longer eventually also dies. And they came up with this idea. It's called weak generational hypothesis. So they treat memory as different kind of memory locations actually. They thought that, okay, we can differentiate the objects in such a way that some of them are young. Everything starts as like junior people in the companies. Then eventually, if you are matured enough in a memory location, which they call young memory location, then they are moved to old locations. But they design their algorithms in such a way that collecting a young memory space is cheap. It can be frequent, but collecting an old memory location is really expensive. So they design or tweak their garbage collection system in such a way that we should not get much old garbage collection going on, which causes actual pauses, long pauses in our system. And generally, young generation is smaller than the old generation space. And there is this concept of promotion, it's called. Every object starts their life as a young or junior object in the young memory location. And by the way, young and old memory locations are contiguous one memory locations. They are end to end. So they are not in different places. It's also important in the sense that since we fragment heavily those locations, it's also a problem. And I don't want to go deep dive into the stuff, but the memory location in young is actually 3 different locations. One is called Eden. Everything starts in Eden. And there are 2 survivor spaces. If you allocate an object, it starts its life in Eden space. And after a while, if Eden space is full or close to full, then our garbage collection system kicks in. It visits all the nodes in Eden. Then it says that, okay, there are some references which are still alive. Then I will put them into one of my survivor locations. Then it's 1. After a while, if Eden starts getting full again, it will kick in again. But this time, it will move the old objects in Eden to survivor location, but first, it needs to keep the track of the old survivor locations, which has count 1. Then, if they are still alive, they will reference count or liveness count will be 2. So it goes on and on and on, and in this example, after 15th iteration, if an object is still alive, it's treated as, okay, this object is mature enough that we can move it to old location. And if we want to visit this object in old location again, the only way to do it is a major garbage collection. But of course, there is a problem. If our young location is not big enough, then if I want to allocate a big memory location, for example, it cannot fit in my young location, then The only space available to me is this old location. And it's called Premature Promotion. Like you get a junior guy, but there is no space left. You put it into seniors and you treat him as a senior guy. The solution is, yeah, increase the size of young place. That's all. And there is another problem with promotion. This is called promotion failure. So you want to promote some junior guys, but your seniors, the old guys, are so full of your company and it's so expensive to get rid of them, you cannot promote the young guys. And it's called promotion failure. And the solution is increase the space of the old one. So it's complementary with each other. And there are some events in our JVM which triggers garbage collection. There are three types of garbage collection. Basically, the minor one is just for cleaning young locations, and major one is just for cleaning the old memory locations. And if we are still unlucky in our system that the system or garbage collection system needs to scan the whole memory, it's called major garbage collection, or full garbage collection, and it's the most expensive one. And in this picture, we can see a trend. Small pikes. What do you think? Are they full, minor, major? The small pikes. They are inexpensive. They are small. They are young memory collections. But once in a while, after this one, it stopped our application and started a full cleaning, and it's the major cleaning. We can see a trend. The memory is going up, 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 and after a while, our application needs to clean the whole memory. And we can go the evolution of garbage collectors in JVM. The idea is the same in all of the languages. For example, Go language treats or market their garbage collection system as the real-time garbage collection. And we will see that real-time is actually comes with some additional costs, and it's basically the other term for concurrent garbage collection. The serial garbage collection, like we discussed before, was the most basic one. Only one garbage collector thread, simplest, lowest memory footprint, the easiest one, but also it's the lowest performant one. It stops the whole application. There is no concurrency going on. It was good back in the days, maybe. And this is one of the examples of the behavior of serial garbage collection. We can use all of these garbage collection in Java just with one parameter of our application. We don't need to do anything in our code, that's all. So we can see that there are 1, 2, 3, 4 full garbage collections happening. And the orange one is the allocated memory. So garbage collection system allocates some memory from our system so that maybe in the future it will need some additional memory. And the blue one is the actual memory usage of our application. And then they saw that, okay, serial garbage collection is maybe not the best strategy. We should introduce some additional threads to do the garbage collection. It still stopped the world because when it starts working, it stops our application and it starts doing the stuff in a parallel manner, but it increases the throughput. And it's multi-threaded old and young collectors. But when they designed the system, the general memory was like 1, 2, 3 gigabytes back in the days. And as we mentioned before, these young and old locations are a huge contiguous memory location. And this is a picture. We can see that this is different. Only one full garbage collection happening in parallel garbage collection, but there is a problem. It doesn't give back the allocated memory. So if you want to deal with microservices kind of stuff, and you are using some Docker containers in hardware, then it's a bit problematic because it will not give back the actual memory it allocated, even if it doesn't use. And they introduced some concurrency. concurrent mark and sweep system. It still stopped the world. It has parallel young corrections, but it can mark the garbage basically. It can visit the mess while your application is running. So in that sense, it's more responsive, but it has its own problems. And this is the behavior of concurrent mark sweep garbage collector. We can see that it can give back the allocated memory, but it still makes a lot of full garbage collections, which brings additional pause times. And then Oracle decided that, okay, I will deprecate this garbage collection system because nobody needs to use it anymore, because we will see that they came up with a better idea. And the common problems of these garbage collectors, serial, parallel, CMS, they are working in a huge contiguous memory location. What can be the problem? If it wants to collect the garbage, it needs to stop your application and it needs to scan your whole memory. And if you think that you are dealing with 10 gigabytes of RAM, so it will take a lot of time. If you have 20 gigabytes of RAM, it will take twice the time. So it goes up and up linearly. It's a problem. So there was a need for a new kind of garbage collector. So these were the generational garbage collectors. Then they came up with this idea. Maybe we can create a system, garbage collection system, which is both generational and also regional. And they created equal spaced memory locations like small rooms, and they came up with garbage first garbage collection system. It's still stopped the world. It stops the world, your application, but like your living room is huge and cleaning your living room in total maybe takes 10 minutes. But if you have small rooms, which kids play in that rooms, then you can clean one room in just 1 minute. Then the kids can continue their playing in the other room. So it's the idea. And the algorithm is designed in such a way that the dirtiest region should be cleaned first. It's the best effort algorithm. Basically, in total, this is the best way to clean most garbage possible in a time frame. Hence, it's called garbage first. First, clean the most dirty ones. And it has a nice feature. It's called string deduplication. If you are allocating strings and if the system detects that you are actually creating a string which is exactly the same you already allocated in your memory, then it can just create a reference to the existing memory location. It doesn't create a new allocation. It's a very nice feature. But still the compaction, the memory layout compaction is still not concurrent. And this is the behavior of garbage first. It starts doing the garbage collection. Okay. It behaves strangely. Then it's smart that it can understand, okay, maybe I can behave a bit more smart. Then it tries to come up with a new idea. Okay, it didn't work that way. Then it tries another one, and eventually it figures out that, okay, this is the best strategy for this application. So Java is collecting a lot of real-time profiling data for all kind of its subsystems, and garbage collection is also one of them. But why it is not cleaning everything concurrently? Because concurrency is an expensive stuff. Alexei Shipilev is the main developer of the next generation garbage collection in JVM, which is called Shenandoah. We will see it. And he is one of the most important figures. And he explains what is wrong with concurrency or what is expensive with concurrency. This is the black box, which is our garbage collection route. Our system starts scanning the references one by one. The black ones are already visited memory references. If they are black, basically it means that our system visited those nodes and we already know that they are not garbage. But when the application is running at the same time with our garbage collection system, maybe our application created a new reference to an already visited node. Normally there was no object reference in this one, and maybe there was a reference in another object, and we deleted that reference in our application because we are working at the same time. And it brings its own cost. And there are some ways to do this kind of stuff. And also another problem with concurrency. We are dealing with different multiple threads, and we want to use the same objects. And also we want to go over the references in the objects, but multiple threads can use different copies of the object, because when we are dealing with concurrency, we need to create an original copy of the object so that we can clean that room, then our application can continue running in another memory location. So these are all additional costs in concurrent memory garbage collectors. And this is the general picture of Shenandoah, next generation garbage collector in JVM. It's almost completely concurrent except some cases. So it's the best one in terms of concurrency. If we take a look at the comparison of different garbage collectors in JVM, we can see that in serial and parallel, nothing is concurrent, and the most concurrent one is Shenandoah and 0GC. 0GC is the answer of Oracle to Shenandoah or vice versa. The difference of Shenandoah compared to garbage first is it's not a generational garbage collector, it's just a regional garbage collector. And we have another one in JVM actually. It's introduced recently. It's called Epsilon Gc. Anybody remember Matrix movie? Yeah, there is no spoon. There is no memory problem. So this garbage collector basically doesn't do anything. It just handles the allocation, and it says that, okay, there is no garbage, no mess, I don't need to clean anything. If you have that kind of a very small microservice, you don't want to introduce additional cost of garbage collection, then you can use this one. Or you can use this one only for testing purposes. And there is this concept of ergonomics. It's coming with the memory layout. These are the different reactions of different garbage collectors. This is G1, and this is G1 again, and this is Shenandoah. Almost real time, it adapts to the actual memory needs of the application. But how do we decide which one to use in JVM? That is the question. It depends. So from the lowest cost to the highest cost, this is the picture. If you want to use the lowest cost possible, and if you have a legacy system, then go for the serial one or parallel one. It depends on your needs, and if you want to make a full reactive system responsive to your users, then basically use Shenandoah or Zero Garbage Collector. Zero Garbage Collector is in Oracle JDK. Shenandoah will always be in OpenJDK. And maybe we can talk about some tips and tricks. So choosing the right garbage collector is the maybe most important stuff for our application. If we need some throughput and the responsiveness or anything is not important for us, then please go for parallel garbage collector. It's the best. If we need some responsive application, we want to do some web pages and the customer satisfaction is the most important stuff, then go for garbage first or Shenandoah. Or if we need a multi-tenancy, Docker images in hardware, go for again G1 or Shenandoah. If you have a large heap, which means that we want to scan the whole memory in short time, then we need a concurrent garbage collector. We don't want to scan and stop everything and continue, then we will lose response. If we have a slow hardware, then we need a concurrent garbage collector. Other tip, immutability. So immutability is already very important. We are trying to promote it always because it's good for multi-threaded applications, it's good for everything, and it comes with an additional benefit for garbage collection. If we have an object like in the picture and it is immutable, by definition, which means that when we create this object in our memory, the references in this object should be created before this object itself. So we can see that this is old, but these are older. So if we imagine that our immutable object is in old location, and since the way of working in garbage collector is visiting the references, and if our garbage collector system sees this object in the old location, it wants to visit all the references going out from this object. But by definition, these are already older than this object itself. So they cannot be in young location. So it's an additional optimization. So garbage collection system automatically skips the reference of immutable objects. So go for immutability. If we already know how many objects do we need to deal with in a collection, please go for that one, because if you take a look at the array list implementation in Java, you will see that by default it starts with size of 10. If you add additional objects, it will grow exponentially, and by default, growing means that there is a contiguous array behind array list, and it will copy everything to another memory location, and all your previous array will be treated as garbage. So you are creating garbage basically. Scope. So in JVM and all of the languages, basically scope is everything. If you are out of the scope, basically the objects which are created in your scope, it can be a loop, or it can be a method, or it can be a class, they all will be garbage. So if we keep our scope small, then basically we will be safe, because it will be treated as a garbage and it will be collected. But if we create 1,000 line of method, everything created in this method will not be able to garbage collected by the system until we go out of that method. So there are cases that we can just chop down the methods into smaller ones, and then we can save, or we can solve garbage collection problems. Unnecessary object creation. We already talked about this one. Everything created in a loop is just garbage. If we want to deal with I/O stuff, then instead of allocating everything inside a file or anything resource, we can use some buffers. And this is interesting. So Java is actually not a full object-oriented language. It has primitives, which are not objects, which are actually native memory locations, let's say, or variables. So a small integer is just 4 bytes in terms of Java, like in C, C++, the same concept. But we have the object counter part of it, which is actually 16 bytes. If you are dealing with millions of objects like integers, bytes, or doubles, please go for specialized collections instead of using list of big integers coming with collections API of Java. And statics, we already talked about it. Static in JVM or Java is always a garbage collection route, which means that it is always alive. It will never be garbage collected. We should never ever create an array as a static variable and put some stuff inside of it. It will always be alive, and it's just creating a memory leak in Java. And we should log our garbage collection activity. We should dump the application output in terms of errors so that we can later analyze them. And we can see there are some practical comments, and that's all. I think, yeah, thank you. I think we are out of time, but yeah, we can get some questions, I guess. What was the system? Any questions? I will be hanging out. Yeah.
Have you tried any theory to analyze the garbage collection log and troubleshoot
Yeah, there are some tools. For example, there is a GC plot open source tool which you can use. Or I have used previously JClarity company's Gensum, CENSUM tool to deal with garbage collection logs to see, and it's smart enough that it can just give you some advice what is wrong. But recently Microsoft bought JClarity company, so I'm not sure about their fate now. And there are some online systems. One is GCEZ, I guess, .com. You can just upload your garbage collection logs, and you can get some nice suggestions. It will automatically scan everything in your log, and it will give you some advice. It's very nice and powerful. I also used it. Yeah, that's coming the top of my head. That's all. Yeah. Any other questions? Thank you. I will be hanging around in ASML booth. If you're interested, just visit us.